everyone. My name is Yasser Malaika, and thank you for all for attending. I'm very happy to be able to talk to you today. So, interaction design in VR. Interaction is turning out to be an essential part of VR as a medium. Because in VR, the content is portrayed in a physically tangible way, it is profoundly satisfying for users to be able to interact with that content. Because the first stages of VR are very taxing on the graphics, interaction represents an opportunity for developers to create truly memorable and satisfying experiences for their customers. It's an aspect of VR that's changing very, very quickly. And one of the most interesting developments over the last few months is the revelation that the first generation of VR systems that are coming to market all aim to provide a very congruent means of primary interaction. That can be described as a pair of handheld devices with very accurate one-to-one tracking in 6 degrees of freedom. So the goal for these devices is to create a kind of rich interaction, a kind of richness that has until now been restricted to expensive research projects. Many people that I've had conversations with have kind of asked me if this sort of standardization is a little bit premature at this stage. But I think there's many positives in this development. First of all, developers can now more easily target multiple platforms. Development for VR is very challenging at this stage, but this congruence facilitates making cleaner design trade-offs and sooner in development. Also, having a shared approach facilitates the kind of broad cultural development of VR interaction, with people grabbing bits and pieces of what they see other people doing and applying them to their projects. That's going to be a very intrinsic part of our earlier VR development. And it's only collaboratively that the industry can develop the kind of conventions, whether through invention or discovery, that will let VR really grow as a platform. These devices are not necessarily definitive. We're definitely going to be seeing change as we learn about how different applications utilize them. Also, they're not necessarily exclusive. We're already seeing lots of projects being developed using more traditional input mechanisms. And by the same token, there are many interesting developments for completely novel interaction systems that are in the pipeline. So we feel it's very important that in these early days that developers develop for multiple platforms. We feel that that helps mitigate some of the risks, and we hope that will allow kind of the market for VR to develop in a healthier way. So some of the things we've learned, we've been using these types of interaction systems for many months now, and now that our development partners have joined this process with us, we have a kind of our first glimpse of experience into this sort of interaction, specifically in the context of room scale VR. And so that's really what this talk is going to be about. One of the first kind of general guidelines we like to tell developers coming from a conventional approach is to sort of think about breaking out their input streams. We're all very familiar with our hands wrapped around a controller, sitting in front of a screen, kind of controlling everything. But in VR, there's kind of a natural mapping of your view to your neck and your eyes. Pointing, manipulation, and actuation maps very naturally to your arms and your wrists and your fingers. And movement maps very naturally to your legs and to your spine as you change your posture. So there's a healthy desire for most VR developers to create intuitive experiences, and we've learned that this kind of approach is intuitive in its own sense, in some ways even more than a gamepad that we're familiar with, because it leverages your users' kind of natural, the natural way they interact with the world on a day-to-day basis. So that's very exciting to us. And another tip we like to think about as we consider these three systems is, and generally speaking, not cross the streams. And I think most people are familiar with how in VR, if you're using, for example, an analog stick to move, how turning or moving can create counter rotations or accelerations that can create an ocular vestibular mismatch with what users' brains expect, making them feel uncomfortable or even ill. So we know to kind of avoid mapping movement to fingers. Also, we know that mapping pointing or interaction with your head can be less than satisfactory. Our neck and eye muscles aren't really well tuned to those kinds of interactions. And also, when you do that, it sort of detracts from their natural task of managing what the user is looking at. But since life imitates art, we found a few instances where actually maybe you do want to cross the streams. One such example is in teleportation. Now in room scale VR, because the physical space is always going to be limited in size, and the virtual space can be unlimited, there's a very strong value in being able to remap or to reframe the physical space within the VR space. And there's a lot of really interesting solutions that people are working on. And one of my favorites is teleportation. You can see in this example, this is sort of a Mars scene. And the way this works is the controller can point, it's kind of like a laser pointer, anywhere within the terrain. And when you simply press a button, the image fades to black, and it teleports you to where you're standing. Before, when we tried this experiment, before we had controllers, we did a lot of this work using your head position. And when we switched to a manual control, we found it to be a dramatic improvement in what users can do. In fact, we found people being able to kind of point sideways to strafe. In other words, pointing to a location where they couldn't immediately see. And you can even point behind your back and move backwards in various degrees. And it really engages your proprioception, the natural body's sense of where the limbs are posed. So it was an interesting experience because it was sort of strange the first time, but it was one of those things that you kind of quickly get used to and then immediately miss when you don't have. And so those kinds of experiences are very interesting for VR. Now we're still exploring these types of mechanisms, but just some quick tips for you exploring teleportation on your own. We've learned that you typically want to avoid rotating the user's view, so that if they're looking forward, you don't want to teleport them looking somewhere else. That can be a little disorienting. Also, it's really useful to have frames of reference between the A and B of teleportation. So if they see something in the distance, and then when they teleport, that same thing is a little bit closer and a little bit bigger, that really helps to anchor the teleportation. Other ideas include showing a scale figure on the landscape where they're pointing to kind of hint at the distance they're going to be traveling. That's particularly important because the sense of depth in an HMD begins to fall off after in a long distance due to resolution limitations. Let's see. Another interesting consideration is because it's so convenient to teleport in places where you're not looking, it's useful to explore ways that you can hint to the user where they're pointing, even if they're not looking directly at the pointing cursor. So some other ways that we've started to kind of think about input in VR. This is kind of a very high-level taxonomy that we've started using internally. It's very different from the kind of low-level taxonomies for interaction that kind of exist in the field of interaction design. But we like to sort of break it out like this. 6 degree of freedom manipulation refers to picking up and moving objects directly within your reach. Pointing works like the teleportation example. It's essentially like holding a laser pointer and pointing it at different objects within the room. You can do so very, very precisely. Traditional hand controls, buttons, triggers, wheels, touchpads. We also have a category for what we call ambient invocation. These are things that are kind of less well understood in the context of VR, but they could include like voice commands. And the last category is sort of subconscious input aspects, such as your position in space, your acceleration, the things you're not necessarily going to be conscious of as a user, but that the game can leverage to do interesting things. And it's very important that these kind of be mapped to kind of the appropriate channel. So 6 degree freedom interaction works best within reach, but quickly falls off when things are outside of your reach. Pointing works really well in your reach and beyond. Actuation with your hand controls is an interesting thing in VR. It works in a very familiar way, but in VR you're using it simultaneously with either pointing or manipulating. And that kind of has a subtle effect on how you want to use things. When you push a button or when you swipe, that can actually affect how you're pointing and how you're holding something. And so it's important to think about how you're expecting the user to use hand controls within that context. Things like the voice control, we've experimented with a little bit. We have a lot of concerns about the robustness of those kinds of systems. We really don't want to kind of yank the user out of the experience. But there's a lot of interesting progress being made with those systems. So it'll be interesting to see how they develop. And for subconscious interactions, of course, it's important that that they remain appropriately within the background. So one of the interesting things we've discovered is that VR kind of has its own system of the Uncanny Valley. And this is not about creepy faces, but that's not to say that you can't have the creepy face Uncanny Valley in VR. That is absolutely a very, very easy thing to do. Anyone who's brought in a 3D character model in VR will attest to that. But in particular, I want to talk to you today about the Uncanny Valley as it refers to interaction. And generally, what this is when a representation becomes less abstract and more concrete. As that kind of moves along the spectrum, we see it tends to create more of an expectation in users that that object behave more like a physical concrete object would, and also kind of a bigger disconnect when it fails to do so. So we're used to understanding the Uncanny Valley for like an NPC on a screen, but in VR there's a peculiar phenomenon where it can start to affect you yourself as the player. And one example is hands. Representing hands is tricky with a handheld device because it doesn't represent the subtleties of your hand as precisely as one would want. Your hands and your fingertips represent a very large fraction of your motor cortex. And so we notice when things are slightly off more so than other body parts. So we saw this with Alchemy Labs in their job simulator demo, but they were able to solve it really well by using a pair of cartoon hands, and these are kind of like large. They kind of feel like large foam sports fan hands that you're wearing in the game. And the interesting thing is they feel sort of less strange than having realistic hands. They kind of really help to ameliorate the expectation that your fingers interact with the physics in the world. And because you have these big cartoony hands, the kind of the clunky game physics become a lot more fun. So representation really matters. It also has an impact, in addition to the player's sense, the level of abstraction can impact their expectations of the world. Also, in Job Simulator, the early versions had a pot where you expected to put ingredients in that had handles. And the pot was represented in a very cartoony way. It was clearly not a real pot, but users frequently expected to be able to pick up the pot, which makes sense because they're picking up all the other things on the table. There's also, not shown here, a microwave in the kitchen with a functional physics door. And at first it didn't really behave as much like a real microwave door as people expected. But again, you'd say, well, it's a cartoon. Why is that expectation there? And then on the other side of the spectrum, there's a refrigerator over here, and that also represented in a cartoony way, worked in a completely non-real manner. It was sort of like magic Star Trek doors, where as your hand approaches, the doors immediately open, and that was totally fine. So there's a really kind of interesting matrix of representation of visuals and interaction. And it really kind of highlights how in VR there's really no substitute for observing and play testing. Alchemy was able to, by the way, fix all of these things as they developed the demo. We also ran into some of these things for the demo we created, the Aperture Science demo. In the pot example for Alchemy represents kind of in interaction design what we call affordances. An affordance is an aspect of an object that kind of can hint to the user what its function is. In the Aperture demo, our representation was intended to be much more realistic. We put a lot of time trying to create enhance the physical realism of how we were doing rendering. We had high-resolution textures. We used normal maps. We used parallax-sensitive environment maps to make our reflections, anisotropic specular highlights. All of those things really helped to make the surfaces feel tangible. There was a point in the Aperture demo when the user is expected to walk up to a wall full of shelves, which you see over here. Unfortunately, it's a blurry image, and to open some of the shelf drawers. And only a few of the drawers were actually interactable, and we used a little tiny red or green light far on the side of the drawer to kind of indicate that. Well, the problem was we had also placed some really shiny, big physical handles, which kind of acted as a much less abstract, much more concrete affordance that kind of totally overshadowed the hint that we were giving the user about whether a drawer was interactable or not. So this is kind of like how in an FPS you never want to place a door with a handle that you can't actually operate. In VR, especially with realistic representations, that becomes even more important. So our tips here are to be mindful of of affordances and how they affect expectations with respect to different levels of abstraction. To choose a level of abstraction that is suited to the experience and the gameplay that you're pursuing, and to be careful about making representational promises that your interaction can't deliver on. Let's see. The more real the representation, the more we start to inherit some of the real-world expectations, and we start to run into the kind of rules that people need to be mindful of when designing real physical objects. And that's not always what we want when we're developing a game. So in that case, we often don't want to get bogged down by the real physical world. Also, with VR affordances, we can make them context sensitive, and we can make them dynamic in a way that you can't in the real world. So lastly, in addition to the player, Uncanny Valley affecting the player and the world, the same representational mismatch can apply to interactions themselves. In VR, we have the chance to make interactions "quote-unquote" real in a way that we can't in other media. One example I like to use is a lever that opens a door. We can kind of expect the player to walk up to the lever, grab it, pull it down, and release it to open the door. It's a very concrete gesture. But something like that, although novel the first time, can quickly become sort of fatiguing, especially if the nature of the interaction is not as directly meaningful to the gameplay as other interactions. I like to ask the question, what is meaningful? And sort of the other end of the spectrum I like to think of is perhaps in a fantasy game where you're mixing a potion. And as you're mixing, you have to be careful not to like slosh one ingredient outside of the bowl, otherwise you'll be wasting material. Or if the exact proportions and the speed that you're mixing it can have an effect on the potion you're making. With that, the gesture then has an impact. It then is meaningful. It's then relevant to the player, and they can kind of make a choice on how they want to approach it. Those tend to be more satisfying and less fatiguing than if you were to say, with the door handle example. Also, it can be more satisfying than, say, having a press A to make potion button in that particular case. So we want to be careful about metaphors with interaction. If we ape the real world too closely, that can start to bring in the limitations of the real world into our virtual interaction. And that is sometimes okay, but sometimes not. It really depends. VR is still a fundamentally computer-based medium. And although it is tempting once we can create these physically tangible visuals to make them too physically real, it's important to think about the users still want to have a kind of an effortless experience in some ways, and there's still a lot of value in providing extraordinary experiences to give people superhuman capabilities. That's an intrinsic part of the value that VR brings to the table as a medium. So I'd encourage you to kind of think about that as you're working on your game loops. So there's a whole bunch of really interesting interaction design rules that are kind of very different in VR. VR introduces a lot of complications. One of them is Fitz Law, which basically talks about the efficiency of acquiring a target and the relationship of the target size and its distance to the pointer. This is kind of well known in 2D interaction design principles, where a more common task or more commonly used button may be larger than smaller one. If something is far away, it requires you to move your hand more quickly, and the difficulty slightly increases. Also, the relationship is a logarithmic one rather than a linear one, so that a small target, if increased by a certain amount, will become easier to hit much more than a larger one increased by that same amount. So some of the complications that VR introduces is a pesky extra dimension. A lot of our understanding and the research into things like Fitz Law have been done in 1 or 2 dimensions and much less in 3 dimensions. We see that when we introduce 2D interaction paradigms in 3D, that users actually will use it a little bit more slowly. And it makes sense because now they have to manage that extra dimension. Also, we're talking about room scale VR. Now it's very easy to kind of place things outside of the user's reach, where now it's not just about reaching out. They also might have to take a step or teleport before something is within their reach, and that's something to be very mindful of. Some of the research that has been done into 3-dimensional Fitz Law suggests that there are differences in efficiency between azimuth changes and inclination changes in terms of usability. And that makes sense because we have elbows, and those mechanics are kind of a fixed constraint for us. So another issue, or complication rather, in VR is what I like to call a bimanual pointer-target ambiguity. And this is when the line between what the cursor and the target are kind of becomes blurry, or even in some cases eliminated. A really good example of that is the tilt brush demo that Skillman and Hackett built for the Vive. In this example, you have one hand which is your brush, and on the other hand you have a palette. So in normal operation, the brush, as you move in 3D space, allows you to kind of paint shapes. And as you point the brush to your palette hand, it transforms into a pointer interaction where you can kind of point at a 2D interface, and you can change the color, change the brush size, undo, that sort of thing. And this is kind of really interesting because you can actually hold the pointer perfectly still and then move the interface under it, completely flipping the relationship of pointer and cursor. And in practice, this ambiguity is totally irrelevant. It's totally natural and totally a very compelling way to use the system. In traditional interaction design rules would say to kind of avoid this kind of ambiguity, but it really works here. So things like that are really worth exploring, and we're interested to see how that kind of changes our understanding of these kind of bimanual operations. Another thing that's really different about VR, especially with respect to like a Fitz Law, is that you have an unbraced and unconstrained field of motion. Typically on a 2D screen, you can take advantage of the fact that you can push the cursor against the edge of a screen or a corner and effectively make use of a larger kind of apparent target size. In VR, we don't really have those kind of constraints other than, say, the floor or the walls, which are kind of only in very special circumstances in play. One really good example of this was Surgeon Sim in ZeroG by Bossa Studios. This was a VR version of their PC game, and it was interesting when they did the port because with a mouse and keyboard, you have kind of a very clunky means of interaction in the 3D world, and that's kind of part of the fun. But then all of a sudden in VR, you have these very precise, carefully tracked objects, and they kind of allow you to be much more precise. So in this game, having everything in ZeroG and having you kind of instantly destroy things and collide with things was really part of the fun. But it also meant that when you moved your virtual hand through the physical world, it would kind of stop and immediately become disconnected. And so that's kind of a really interesting problem, is how do you represent a physical constraint to the user that isn't physically there. This actually ended up working really well for Surgeon Sim because of the expectation of being clumsy. So there's a lot of cases where your game may be able to take advantage of that, actually. So, and finally, there's a big difference between 6 degree of freedom near-field interaction and pointing. Pointing in VR does conform much more to what we understand about how Fitz Law works. But of course, you don't have the constraints. Also, it's important to note that if you are working with a pointing type interaction, that you really want to take account of translation as well. If you use rotation only, it can kind of introduce some acceleration mismatches between the wrist and the elbow. So we've found that including translation really helps create a natural pointing interaction. So next up, I want to talk to you about haptic feedback. And we found that that's one thing that can really elevate a VR experience. In physical reality, when you reach out and you touch something, when the touch registers, we believe that helps to sort of anchor your proprioceptive system, so that your body kind of understands that that's where that thing is on a very visceral level. And this can really help to improve spatial awareness of the environment. So one way people do that is using the Haptic Pulse mechanism and the touchpad on the Vive controllers. It's really also useful to use it kind of as a hinting mechanism. You can think of a mouse cursor as you move over a button. When the cursor changes, you can think of those changes as an opportunity for a haptic pulse. So mouse over, mouse out, when you press and when you release can all be kind of augmented with the haptic system. And that's really interesting when it's done well, because it can, as I said, our hands are so, it can feel with such richness that you can start to almost offload some of that hinting to your purely to your sense of touch, and that can help kind of free up your visual and auditory input channels in other ways. Also, haptic feedback can be really interesting for conveying a sense of texture in the space. If you imagine, since I have an object that's tracked one-to-one, I can measure like every 5 millimeters or so, I can trigger a haptic pulse. And that has a very interesting quality of giving texture to open space that you don't have otherwise. And you can do interesting things with that. For example, we have an example of a longbow demo, where as you pull the bowstring back, the frequency and the amplitude of the haptic pulse changes as you move back and forth. And even though you don't feel any force, it can really convey a sense of elasticity. So friction and mass or other things you can sort of kind of fake with a sense of touch in a very compelling way. And the last interesting thing that we've seen with haptics is sort of using it like a vibrating phone. And this was done very well in the tilt brush demo, where in the beginning of the experience, your brush activates and there's a little call out in your controller that kind of explains first-time users what it does. But oftentimes, people are holding their controllers outside of their field of view. So this is kind of an effective sort of tap on the shoulder. It says, hey, there's something interesting going on. And again, that can help keep the visual and auditory input channels focused on what works well for them. So say you've made a lot of progress and you're doing a great job with your VR experience, and your player is totally immersed and focused on what they're working on. Well, now you have a new enemy, which is inattentional blindness. And probably most of you at some point have watched that video on the internet where You watch a group of college students playing basketball, and the video asks you to count how many times a player with a white shirt throws the ball. And so you watch the video, and it turns out that in the middle of the video, somebody in a gorilla suit walks into the middle and waves their hands around and then walks out. And researchers have discovered that very few people actually notice the gorilla in the middle of the scene. And that just reflects a normal human tendency to when we're focused on something and we're giving it our full attention, oftentimes we can miss stimuli that is right in our field of view. So everybody here has probably thought about VR experience, and when things are kind of outside the camera's field of view, or making the player turn their head to look at things behind them. But we also have to think about the complexity of the imagery and the user's focus to make sure that they're seeing what we want them to see right in front of them. Or we can leverage this inattentional blindness for nefarious purposes. There's all kinds of interesting research going on to see how we can alter people's perception of the virtual space by taking advantage of our natural inattention. So because VR is so immersive, it really helps to think about a lot of the traditional interaction design concepts. Cognitive load is one of the issues, also sometimes referred to as mental friction. There's many different types. When you ask a user to translate from one mental model to another, when users have to shift their focus from many different points, also when users are expected to remember an arcane sequence of commands that can introduce cognitive load, and also having to piece together new knowledge. All of those things done at the right time and with the right pace can be really satisfying. But with VR, you kind of have a different use of bandwidth to the user, and it's really interesting when you're running your play tests to sort of think about the context of cognitive load. Also, the flip side of that is what we call performance load or kinematic friction, and this refers to, like I mentioned before, expecting the user to grab the door handle and flip the lever every time they need to open a door. Sometimes, if you approach things more from the sense that what is the user trying to accomplish, if you can use their gestures to kind of indicate intent rather than making them physically work for it every time, that can be a way to kind of improve the efficiency and the satisfaction of the VR experience. Also, invocation loading is something we think about. In VR, you don't have a keyboard full of hotkeys in front of you. The buttons on the controller are much more limited. And so that's something we need to think about. How can we provide the same level of choices, or how do we manage the number of choices that the user has? And also another thing that can affect kinematic load is error handling. If the user makes a mistake, do they have to start over from the beginning, or can the system accommodate fixing up a little piece of the interaction in an out of order way? Finally, one of the last guidelines I have to share with you today is to bring the interaction to the user, not vice versa. We talked a little bit about when a lever is subtly out of their reach, but this also refers to the quality of VR, that it's really rooted in physical space, much more so than what we're used to. People who will be using VR are of different heights, obviously, and that has a direct impact on their physical reach. And also, for room scale VR, they were going to be, walking around rooms of very different sizes. So that's something to really think about the games industry has been working on accommodating people with different abilities in many different ways. And in VR, it becomes an issue right at the very beginning because it is inherently about that physical space. So with that, I'd like to thank you and also open it up for questions, if we can. And if you have questions later or would like to talk to me afterwards, I'll be available in the back as well. Over here.
Hi. The Valve Vive system, the specialty is that you place your lighthouses in a room and the gamer will act in a real room. And that's opposed to Oculus, who say the first experience will be a seated experience. Do you think that the Valve VR system won't be a seated experience in the first generation? And aren't you afraid that you're going to become the next Kinect? So that in the first place, everybody wants to buy it, and then they say, oh, I don't want to move all my furniture to get a VR experience, so that you then have to get back to a seated experience.
Yes, that's a great question. So my understanding of your question is, do I think the Vive is going to work as a seated experience? And absolutely it does. I use it every day in my office as a seated experience. And the nice thing about Lighthouse is it really scales very, very nicely. You can totally imagine somebody doing a driving sim or a space combat sim. It tracks just as accurately as a seated experience. If users want to do it primarily seated and then kind of stand up and not walk around, that also works very well. And if they do have that space and want to dedicate it, they can choose to do so. That's an interesting thing that developers are going to have to think about, is how do we accommodate those different needs. But it does absolutely work as a seated experience. So it's not an either or. In fact, one of the things that I'm most excited about with the Lighthouse system is having converting my dining room table and having all my friends seated around the dining room table, having a shared seated experience, which you can do in a large volume space. I think there's a lot of potential for rich experiences in that context. Over here.
As you described, the shared experience of friends and peers at a table, have you already had examples and tryouts with such interactions? And how would they have impacted this kind of closeness which you would have required to make another's interaction meaningful?
Yes. So the question is, have we tried multiple people in one space? And yeah, it works just like a networked game. It's very interesting because when you're with somebody in that shared space, kind of all the natural rules of personal space start to apply. And I think that's also one of the strengths of Lighthouse, because the Lighthouse devices are not really connected to your computer. They're sort of passive devices, and they sort of project an absolute coordinate system in the volume of the space. So, two people on completely different computers share that coordinate system. So if I hand you a controller, it's registered in the same exact space as my headset and your headset. And I think that's going to be one of the strengths. And it's really interesting too that when somebody picks up a headset and puts it on, it basically works like a high-end motion capture system. And in the same way that a motion captured cartoony animation all of a sudden kind of feels alive, even just with a headset, you can get a sense of somebody's posture, if they're standing on one foot or the other, and you can almost even identify who that is just seeing that floating HMD, and it gets better with the controllers. So yes, that works very well, and I think that like all kinds of multiplayer experiences, that's going to be a really satisfying space to explore. Yes?
So you talked a lot about hand tracking controllers. What are your thoughts on traditional input devices like mouse and keyboard, or let's say joystick? So say a flight simulator experience where you have very complicated input control. Do you think that works in current generation of VR, or are there certain ways to handle that better?
Yeah, it absolutely works. And in the beginning of my talk, I mentioned that there's a lot of really compelling experiences being created using those traditional input methods. But because we're not thinking of VR as an exclusive standing system, it works totally fine at your mouse and keyboard, or in a cockpit with hands on throttle and stick. You can register those devices in your virtual space, and it works pretty well. So I think it really depends on the experience you're trying to create. Really, there's the reason we're sort of favoring the hand controls is because we feel that that's kind of a piece of the puzzle that wasn't easily accessible. So we feel that it's important for every customer to have that kind of out of the box, so that developers can feel confident that they can explore VR specific kind of novel experiences. But by the same token, it doesn't by any means mean that we can't do the other input methods. And in fact, I think that adds to the richness of the ecosystem. And it's one of the reasons we like the PC as a platform, because you can add a Kinect camera to a joystick or a keyboard, and have your friend doing an asymmetric gameplay with a controller. I mean, it's a wide open space.
Yeah. So what do you think about augmented reality, and which rules do you think apply to like a HoloLens or something like that? And what do you think about the future if like augmented reality is going to take over VR?
I'm very excited about AR. In fact, one of when the hardware team at Valve first started working in this space, we were really working on the two problems simultaneously. And there's a lot of excitement about the possibilities of AR. The reason we chose to kind of move in a more VR direction is because we felt that it was kind of a more tractable problem. We could bring something to market sooner with the current technology, and we could start to learn about the parameters of that idea space. The AR we felt was a little bit more technically further into the future to really provide the high quality experiences we wanted to create. And also, secondarily, we had done a lot of experiments where we scanned in a room and put that in VR, so that we were in kind of a virtual representation of the actual space we were in. We call that AR in VR, and that actually works really well as well. So there's a lot of interesting things coming down the pike with video graphics chips that do a lot of the optical processing in a programmable way in silicon that will enable a whole bunch of interesting applications for bringing the real world into VR. There's a lot of possibilities. And one of the nice things about how these technologies are developing is For example, a lighthouse tracking system could conceivably track an augmented reality headset in a room scale environment just as well as a VR HMD. It's really interesting to see these technical pieces kind of come into play, and we think that if we can develop a successful marketplace around a core, that these will be able to expand, and people will be able to experiment with them. So yeah, I'm excited about AR too. Okay, thanks a lot, everybody.